Sánchez-Gabites from the Universidad Complutense de Madrid. And he's going to talk about obstructions to realizing toroidal sets as attractors. Please, Jaime.
So thank you, Leticia, and well, greetings from Spain to all of you. I'm sorry I couldn't make it to be there. It would be a pleasure to be there, just to meet you in person and also to go for walks in the sort of forests around that level, which is really nice. But well, traveling with this coronavirus and so on didn't seem advisable. So well, anyway, I'd like to thank the organizers for inviting me to give this talk, and also for their efforts in coordinating these online and offline talks, which I guess has to be a bit unnerving, I guess, but they are doing a brilliant job. So thank you very much. And of course, I'd like to join my colleagues in wishing happy birthday to Felix, who also was really kind to me, providing information via email. So so thank you, Felix. All right, let me set a timer so I don't bore you to death, or at least I do so for a limited amount of time. Okay. So I'd like to talk about this topic, which is well, it belongs to a sort of very general problem of trying to understand how complicated, from a topological point of view, an attractor can be. I'll give definitions in a second. This is joint work with Barge, who works in Madrid in the Universidad. So let's see if this. So as an introduction, well, we all know that attractors of dynamical systems can have a very complicated topological structure, and actually they are called strange attractors. And the question is how complicated this structure can actually be. So a little more formally, so if I'm given a compact subset of some space, I'm gonna work almost always in R3. So you can think of M the R3. So given a compact subset of R3, if you wish, does there exist a dynamical system on R3 which realizes the compact as an attractor or not? So do there exist sets that are so complicated that they cannot be replicated as attractors by some dynamical system? And we would like topological answers. So we would like to, ideally, we would like to be able to characterize topologically for which compact sets, which compact sets can be realized as attractors. So that's far too much. This is a really hard problem, and we'll only obtain partial answers. And but one of the things, or one of the key messages that I think I'd like to at least convey in this talk is that it's actually not the topological properties of the compact set itself, but rather how the compact set sits in the ambient space, what actually determines or seems to be very closely related to whether it can or it cannot be realized as an attractor. And we'll see, we'll emphasize this later on with an example. And of course, I'm being very vague here because, well, you can formulate this realization problem for, say, continuous dynamics, that is flows, or discrete dynamics, or even iterated function systems, as in the previous talk. You could formulate the problem for invertible or non-invertible dynamics, allow various spaces M, etc., etc. So there are many variations of this problem. So the first thing that I would like to do is to actually focus on a very specific situation. So we're going to consider discrete dynamical systems and actually invertible discrete dynamical systems. So the dynamics are going to be generated by a homeomorphism F. And I'm going to consider stable attractors. So this is just a reminder of the definition, because there are many definitions, many different definitions of what an attractor is. So for me, an attractor is going to be a compact set. So they are always going to be compact. and they are going to be invariant, and they are going to attract compact subsets of some neighborhood of the attractor. So there exists, as you can see in part 2 of the definition, so the attractor K has a neighborhood U, such that K attracts every compact subset of U. And by that, I mean that if you start with any compact subset of U, P, capital P, and you start iterating it with the dynamics, then it eventually enters any prescribed neighborhood of the attractor. So perhaps you're more used to requiring that the attractor should attract points rather than compact sets. But this definition is actually a combination. So when you have an attractor which is stable in the sense of the upper node, then it not only attracts points, but it also attracts compact sets. So in order to simplify things, I just stated the definition directly by requiring that the attractor attracts compact subsets. And the maximal U, the maximal neighborhood, such that the dynamics, such that the attractor attracts things in U, is called the basin of attraction of the attractor. I will say it again later on, but I'm not assuming that the attractor must be global or anything. So the basin of attraction of the attractor can be whatever. It needn't be the whole free space. And of course, there are analogous notions for flows, where the time, instead of being discrete, runs over the real numbers. These definitions, I think, are pretty standard. So let me give you some examples of things, of compact sets that can always be realized, or well, yeah, always be realized as attractors for some dynamical system. Well, the easiest one is you can consider a finite simplicial complex in some Euclidean space, and it can always be realized as an attractor for a flow, and therefore also for a homomorphism, just taking the time one map of the flow. And the idea of the proof is that you can thicken the simplicial complex. Technically, you take a regular neighborhood of the simplicial complex, and using the structure of that simplicial, that regular neighborhood, you can construct a flow which is stationary outside the neighborhood, which is painted in blue in the screen, and pushes and it's also stationary on the attractor, which is the sort of triad, black triad, and otherwise pushes everything onto the attractor. So this is perhaps the simplest situation, and the trivial generalization of that is when you have a tame compact set. So tame is a notion that comes from geometric topology, and we will, as the talk progresses, we will encounter more and more notions that come from geometric topology. So tame just means that there is a homomorphism of Rm, so of the whole ambient space, that sends K onto a simplicial complex. So up to a homomorphism, K is essentially a simplicial complex. And of course, you can use that homomorphism to turn K into a simplicial complex, then use the first example to turn that simplicial complex into an attractor, and then you use the inverse of the homomorphism to turn the original K into an attractor. So tame sets are also realizable as attractors. By the way, I didn't say this, I forgot to say this, but as I am aware that this is a conference on dynamical systems, I'll skip many thorny details about topology and geometric topology and so on and so forth. So my goal is rather to give you an idea, a general idea of the techniques and the sort of results that one can obtain, and not enter into the thorny details because they can get really quite thorny. So those two examples were more or less trivial. Now here is another example which is a little more complicated, but it's also quite neat. So what about the realization problem in R2? So what compact subset of R2 or manifold can be realized as attractors for some dynamical system? Well, you can see a proposition there. I haven't said who, I haven't written the author of the proposition because I think it's more or less like folklore or something. I don't know. So the first thing that we see is that something a little strange happens in that points 1 and 2 say that K can be realized as an attractor for a flow if and only if it can be realized as an attractor for homeomorphism. So in this case, both problems are the same. And part 3 gives a topological criterion for this realizability K as an attractor in terms of the check cohomology of K. So if the check cohomology of K is finally generated, and only in that case, then you can realize it as an attractor, either for a flow or a homeomorphism. And part 4 is just a translation. If you're not very comfortable with check cohomology, part 4 sort of translates part 3 into a more elementary language. And so there's a rather particular feature of this result in that whether K is or not realizable as an attractor depends only on the topological properties of K. It doesn't depend on how K is embedded in R2. And that is clear from part 3, because it's a cohomology of K is a topological invariant of K alone. It doesn't, it isn't related at all to how K lies in R2. This is very particular, very specific of 2 dimensions. And as soon as we move into 3 dimensions, and this is our next example, the situation changes and becomes more tricky. So let us consider the realization problem for global attractors in Euclidean space. So what I want to ask, or what I want to find out is, given a compact subset of some Euclidean space, when can it be realized as an attractor, either for homeomorphism or a flow, which has whose basin of attraction is the whole Euclidean space. This is a variation on the original problem. And this proposition is due to Garay. I think it's back in the 70s, 90s, no, 90s, I think. Yeah. And as you can see, there are, again, parts 1 and 2 say that the problem for flows and for homeomorphism is the same. And parts 3 and 4, let's postpone 4 for later on, because it speaks of cellularity. And if you look at item 3, it says that K can be realized as an attractor, as a global attractor, sorry, if and only if it is point-like. Point-like means that the complement of K, so when you remove K from Euclidean space, what you get looks exactly the same as if you had removed a single point from K. So, for example, if you have a round ball, if K is a ball, round, nice ball, you remove it from Euclidean space, what you get is essentially the same as if you had removed only the center of the ball. Or if K is an arc, straight line, you get the same thing. When you remove it, the thing that remains is homomorphic to the thing that would remain if you had removed just a point. So it's not completely clear. I'll give you an example now, but this suggests that the answer to the realization problem now depends not only on the topology of K itself, but also on how K sits in our N. Because as you see, we are making reference to the complement of K in our N. We're giving a condition of the complement of K rather than on K directly. And this is the typical situation. So let me give you an example to clarify this. So consider these 2 arcs in R3. So you have the first one, K1, is just a straight line. It's boring arc. And the second one is a classical arc. It's called, well, the Fox-Artin arc. And it has amazing properties, topological properties. But it's also, so although the drawing doesn't show it, it suggests that the arc sort of extends and eventually joins P1 and P2. So even though it is embedded very weirdly in R3, but it's an arc. I mean, it's homomorphic to K1. So K1 and K2 as topological spaces are the same thing. They are both arcs. However, K1, so the first arc, the boring one, is realizable as a global attractor. That's actually, you can imagine the flow intuitively, but K2 is not realizable as an attractor. And the reason is that its complement, as a global attractor, sorry. The reason is that its complement is not homomorphic to the complement of a point, and that's because if that were the case, if the complement of K2 were homomorphic to the complement of a point, they would have the same fundamental groups. Now the complement of a point is simply connected, so R3 minus K2 should be simply connected, but it's not. Yeah, that's a non-trivial fact, but it's true. And so, as you can see, we have this emphasizes the idea that I was telling you earlier, that you have the same object, so K1 and K2 are both arcs. However, they're embedded differently, and one of the embeddings, the wild one, the Fox-Hartin arc, is so wild that it prevents the arc from being realizable as an attractor, global attractor in this case. And just as a curiosity, let me go back to the previous slide. You can see that the Fox-Hartin arc consists of two symmetric halves. Now, if you thought only about one of the symmetric halves and you discard the other one, you still have an arc, and that arc actually can be realized as a global attractor. So both of the halves, independent, so if you take any one of the two halves of the arc, the Fox-Hartin arc, independently, it can be realized as an attractor. But when you take the union of the two, it cannot be realized as an attractor anymore. So this is quite a surprising thing, because it shows that the problem is rather delicate. The problem is not exactly the fact that we have this sort of infinite knotting towards P1 and P2, because if that were the only obstruction, then when we took one of the halves, we would still have that infinite knotting, and we shouldn't be able to realize it as an attractor, but we can. So it's a quite delicate thing. Okay, so let me give you some trivial, very, very trivial remarks, but just to sort of pause for a moment and organize our ideas. So if K can be realized as an attractor for a flow, then of course it can also be realized as an attractor for a homeomorphism, just taking the time one map of the flow. But the converse is generally not true. So for instance, the dyadic solenoid is I'll recall what that is later on, but it can be realized as an attractor for a homeomorphism, but not for a flow. So in that sense, the sort of the class of compact sets that can arise as attractors for homeomorphisms is bigger than that of flows, and it's in some sense it's more interesting. I'll tell you a little more about it later on. And points 3 and 4 are really trivial, but I just wrote them to emphasize the idea that we are we will not be interested in global attractors, because we have already seen that the question is solved on Garay in terms of this point likeness of the compactum. So we will be interested in compacta that may be realized as attractors, but not necessarily global. And of course, the two problems are different, because, for instance, a simple closed curve, you can realize it as a local attractor, but not as a global attractor. So just to clarify something. Okay, so what are these toroidal sets that appeared in the title of the talk? Well, one of the characterizations of global attractors from Garay's theorem, you might remember, it was the last part, talked about cellularity. It mentioned cellularity. And that's, again, a classical notion from geometric topology, and you can see the definition there. Compactum is called cellular if it has a neighborhood basis of closed M cells, where closed M cell just means a set which is homomorphic to the closed unit M ball. So it's a ball, but it's not round, if you wish. it could be deformed. So why are global attractors cellular? We call that Garay's theorem, said that an attractor, a global attractor, must be cellular. So this is very easy. So if you have a global attractor, then you can, of course, it's a compact set, so you can pick a huge ball, B, that contains the attractor in its interior, and then you can iterate the ball with the dynamics. So since F is a homeomorphism, we are thinking of invertible dynamics. What you get is a collection of balls, so that those iterates Fn of B, a collection of balls, and it's a neighborhood basis of the attractor. Why? Well, because the attractor is an attractor. And so the balls, the original ball B was contained in the region of attraction. And so when you iterate it with the dynamics, it gets sort of shrinked towards the attractor. So that provides you with the neighborhood basis of the compactum, which is comprised of balls of cells. So that the compactum is. So in general, here let me remark that it's essential for this argument that K be a global attractor, because otherwise we could try to mimic the same argument, to repeat the same argument, but we would have to choose B to be contained in the region of attraction of the attractor. And in general, there is no guarantee that if you have an attractor, you can always find a ball that contains the attractor and is contained in its region of attraction. That's not true in general. So that's why, in general, this argument doesn't work. So from now on, we're going to set ourselves in R3. Why not R2? Well, because we already saw that the problem is sort of trivial in that case. And why not R4 or higher dimensions? Well, because the problem becomes even more difficult. So R3. The motivation for the definition of a toroidal set is precisely the definition of a cellular set. So as we said, a cellular set is a set which has a neighborhood basis, which is comprised of cells. Cells which are homomorphic copies of a ball. And you can think of a ball as something of a handle body, if you wish, to be a little pedantic, handle body of genus 0. It has no holes. So if you want to ramp up your complexity, you could consider handle bodies of genus 1. So that's solid toroid. So you can define or say that a compactum is toroidal if it has a neighborhood basis of solid toroid. So this would be sort of the next step in complexity. Cellular sets have neighborhoods of cells. Toroidal sets have neighborhoods of solid toroid. And well, I have it there that it's toroidal if it has a neighborhood basis of solid toroid, and it's not cellular. Just to exclude that sort of case, which would be trivial for no person. So let me give you some examples of toroidal sets. So any polyhedral simple closed curve is a toroidal set. And the only thing that you need to do is just thicken. So you imagine that the simple closed curve, because it's polyhedral, you can imagine that it's made of wire or something in space. You just put a thick coating of paint on the curve, and you obtain, so you thicken it up, and you obtain a solid torus, which is a neighborhood of the curve. And by putting a very small amount of paint, you can arrange that the torus is very, very thin. So you do indeed obtain a neighborhood basis of solid toroid. Now the condition that the curve should be polyhedral is crucial because that's what allows us to thicken the curve up. If you are not happy with piecewise linear topology, then you can think of a differentiable simple closed curve, and then you take I can't remember the name. The analog of regular neighborhoods in the context of differential topology. So, and in the second example, so those examples are not very interesting. Now, the second example is more interesting. So, you can see a drawing there, which is an infinite connected sum of knots. So there's a piece of string, and there are many nodes. There's actually a whole sequence of nodes, and their size decreases as we move to the right. And so that's actually, in the abstract, that's a simple closed curve. It's homomorphic to S1, but it's embedded in a weird way in our code. So this is actually a wild, it means not tame, simple closed curve, and it's also a toroidal set. So why is it toroidal? Well, because you can construct a neighborhood basis of the curve, which consists of solid tori, and you can do that by, as suggested in the picture, so you can consider solid tori, Tn, that follow k up to the nth summand, and then swallow the infinitely many remaining nodes. So the torus that I've drawn, it's shaded gray in the picture. As you can see, it follows closely the first two nodes. And then when things get thorny and we approach the sort of wild part of the arc, we just swallow the nodes. And T3 would be the same, but it would follow closely the arc up to the third node, and so on and so forth. And so you can obtain a neighborhood basis of solid tori of this arc. So this arc is, arc, it's not an arc, yes, this node, so this simple closed curve. So this is again a toroidal set. More toroidal sets. Well, the dyadic solenoid, or in general, the n-adic solenoid. So this is a classical example of an attractor, and it can be constructed as the intersection of a nested sequence of solid tori, each of which winds twice inside the previous one. So I've tried to suggest a construction there. I'm sure you all know it. And by its very definition, the solenoid, which is the intersection of this decreasing family of tori, by definition, it has a neighborhood basis of solid tori, which are the actually key. So every solenoid is actually a toroidal set. So those are some examples to try to illustrate that toroidal sets actually include some interesting objects. Now, what is going to be the difference between cellular and toroidal sets beyond the definition? I mean, heuristically, what's the difference? Well, in a cellular set, as recall that it means that the set is the intersection, or it's the intersection of a decreasing family of cells. Now, placing a cell inside another one is actually a very boring thing to do, because there's only one way to do that, essentially, up to homomorphism. So in some sense, cellular sets inherit that sort of boring nature. Well, I must say that if there is some topologists, some geometric topologists in the audience, please forgive me, because I'm saying that cellular sets are boring, and they are not boring at all. But they are sort of, well, they don't have the features that I'm interested in. So what's the difference with toroidal sets? Well, in a toroidal set, you have the toroidal set is the intersection of a decreasing family of tori, of solid tori. However, there are many ways of placing a solid torus inside another one. And in particular, you can wind. So here T2 winds twice inside T1. That's something that you cannot do with cells. A cell cannot wind inside another cell. And you can knot like this. A torus can be knotted inside another. So these two new features, knotting and winding, suggest that toroidal sets are going to inherit some sort of amount of knotting and winding. So we will actually introduce two magnitudes that capture these ideas. So as a very coarse measure of the knotting involved in the construction of a toroidal set, we'll introduce the genus of a toroidal set, which is a sort of generalization of the genus of a knot. And as a measure of the winding that is encapsulated in the toroidal set, we'll talk about the prime divisors of a toroidal set. I don't know if I'll have time to talk about all these things, but I'll try. So Before doing that, because these are just topological things, before doing that, let me go back to the realization problem to explain, or just to sort of motivate why this winding and knotting phenomena might play a role in the realization problem. So consider for a moment the problem of realizing some given toroidal set as an attractor for homomorphism. Maybe it can, maybe it cannot. So imagine that it can. So suppose that a toroidal set is an attractor for a homomorphism of alpha. Recall that we are not assuming that the attractor is global, so we only know that K attracts compact sets that are near K, but we don't know how close they need to be. We have to be contained in the region of attraction, which we'll call U. So since K is toroidal, by definition, it has a neighborhood basis of solid tori, and in particular, there is a torus which contains K and is contained in U, basin of attraction of K. And then, iterating this torus, we obtain a neighborhood basis of the attractor. And well, as you can see, I've written there exists K, such that blah blah blah. That's just to ensure that we obtain a nested sequence of solid tori. So that's just a standard, completely standard manipulation. So the takeaway message is that when you have a toroidal attractor, you can always manufacture a very special neighborhood basis. I've underlined it because I will use the same terminology later on. So you obtain a neighborhood basis which consists of nested solid tori, such that all come from iterating the initial torus T. And therefore, they are all ambient homomorphic to each other. And so they are all equivalently knotted. And all consecutive pairs of tori are homomorphic as pairs. So each torus winds inside the previous one exactly the same number of times. So this is a sort of rigidity property in the sense that in principle, there is no reason to expect that an arbitrary toroidal set should have a very special neighborhood basis like this. So very roughly, these two things suggest that for a toroidal set that can be realized as an attractor, the amount of knotting in the toroidal set should be finite, and the amount of winding should be, well, I've written it there. At this stage, it's probably not very easy to understand what I mean, but it's sort of exponential with a fixed base n, big N, capital N, and the prime divisors of these winding numbers do not depend on n. So this all sounds very, very, very vague. I'm aware of that. So, but it sort of points into the general direction that I want. So our next goal is to formalize these ideas. So to define the genus of a toroidal set, which measures the amount of knotting, and the prime divisors of a toroidal set, which measure the amount of winding, and then show that when a toroidal set is realizable as an attractor, these two objects, the genus and the prime divisors, have some finiteness property. And use that to produce examples of toroidal sets that cannot be realized as attractors. So that's the plan. So let's focus first on these knotedness properties of a toroidal set. And let me review very quickly the classical idea of the genus of a knot. So here, let K momentarily, I've been using K to denote toroidal sets. Momentarily let K be a polyhedral knot in R3. And its genus is a non-negative integer which measures somehow how the amount of knotting of K. So for example, you can see the unknot, which means a string that is actually not knotted in any way. That has genus 0, and it's actually the only knot that has genus 0. And the trefoil, for instance, which is the simplest knot, the simplest non-trivial knot that you can find, has genus 1. And well, I've given you a definition there. You don't need to know it. If you don't know what a Cypher surface is and so on and so forth, don't worry. It suffices to know that genus is something, it's an integer that you assign to each node. And ambient homomorphic nodes have the same genus. So usually when you have two ambient homomorphic nodes, you actually consider that they are the same, barring some considerations about orientation. Okay, so we would like to extend this idea, which is the genus of a knot, to the genus of a toroidal set. So it's actually quite easy to do this. No? So first, define the genus of a solid torus as the genus of its core curve. So you have a solid torus, and along the middle of the torus, you have what we call a Kerr curve. So you can actually think of the torus as a thickening of its core curve. And that Kerr curve has a genus because it's a knot. So the genus of a toroidal set is the smallest non-negative integer G, such that K has arbitrarily closed neighborhoods, which are solid tori of genus not bigger than G. So in other words, if you have a toroidal set, and then by definition, it has a neighborhood basis comprised of solid tori. And then if you can find a neighborhood basis comprised of solid tori whose genus is less than, say, 50 for each of those tori, then you say that the genus of the toroidal set is less than 50. And if no such G exists, then the genus of the toroidal set is defined to be infinite. Or in other words, if whichever basis of neighborhoods you take, you actually see that the genera of the solid tori of the bases are not bounded above, then the genus of the toroidal set is defined to be infinite. So this definition is quite natural, but it's, at least in principle, it's difficult to compute because usually we have, when we are working with a toroidal set, we define the toroidal set as the intersection of a very particular family of solid tori. But to compute the genus, we would actually have to examine all possible bases of neighborhoods of the toroidal set. So let me skip this one for a second and then I'll come back to it. So how do we compute the genus? Well, there's actually a theorem which says that you can compute it with this formula. So you can choose any neighborhood basis of K, whichever basis you want, comprised of solid tori, and then compute the genera of those tori and compute the limit. And that limit will give you the genus of the toroidal set. Or if you wish to think of this theorem in a different way, what this theorem is saying is that the limit is independent of the neighborhood basis that you choose. The proof uses classical ideas about knot theory and satellite knots and companion knots. So, for instance, let's look again at this wild knot. So remember, it was sort of a connected sum of infinitely many nodes, and we knew how to find one particular neighborhood basis of nodes, which is comprised of solid tori. And we did that by sort of following closely the first n nodes and then swallowing the remaining nodes. So if you look at T2, for instance, in the screen, that follows closely the first and the second nodes, and it swallows the remaining nodes. Now, the genus of this torus T2 is very easy to compute because the genus is additive and a connected sum of nodes. So the genus of T2 is actually the genus of the first node, which is 1, plus the genus of the second node in the sequence, which is 1 also. So the genus of T2 is 2 in this case. And if you continue in the same fashion, you would see that the genus of Tn, the nth torus in the basis, is at least n. In this case, with this particular drawing, it would be exactly equal to n. And therefore, the limit of these things is infinite. So the genus of this toroidal set is infinite, which means translating it back to a more sort of less pedantic language, it means that if you take any torus, any solid torus, which is a neighborhood of this K, and the smaller it gets, no matter how cleverly you try to construct the torus, the closer it gets to K, the higher its genus has to be. Which seems quite reasonable looking at the picture, but this is the proof. So why are we interested in the genus of a toroidal set? Well, let me come back here and let's look at this key property. So if a toroidal set K is realizable as an attractor, then remember that we said that we could always construct a very special neighborhood basis, which had the property that all the Tn, all the torus in that, the tori in that basis were ambient homomorphic. So in particular, as nodes, they are the same nodes, and they all have the same genus G. So in particular, choosing that particular basis to compute the genus, what we see is that if a toroidal set can be realized as an attractor, then its genus is actually finite, must be finite. So coming back to this example, this one node has an infinite genus, and therefore you cannot realize it as an attractor for a homomorphism of R3. There's no way to construct a homomorphism of R3 such that this node is an attractor. Without saying anything about its basin of attraction. The basin of attraction could hypothetically be very weird. We are allowed to do all sort of weird things, but even with that amount of freedom, there's no way that we can realize this thing as an attractor. Let me remark that if we didn't have this infinite sum of nodes, but only a finite amount of them, then the set wouldn't be wild, it would be tame, and we could realize it as an attractor for a homomorphism. So again, we have this idea that the same abstract topological object, in this case just a circle, can be embedded in different ways in R3 in such a way that some of those embeddings cannot be realized. So let me see how I'm doing on time. Okay, so 9 minutes. Okay, what about winding? Well, recall that we mentioned again that if we can realize a toroidal set as an attractor, then we could construct this very special neighborhood basis where all the tori were equivalently noted. We have also already used that to define or to use the genus. And also in that very special neighborhood basis, all the pairs were homomorphic to each other. And so in particular, if the smaller torus will always wind the same number of times in the bigger torus for each pair of consecutive torus. So how can we exploit that for our dynamical purposes? Well, let us go back to topology first, and then we'll use it in dynamics. But then first, a little bit of topology again, geometric topology. So how are we going to measure the winding? So imagine that you've got a solid torus. Look at the drawing. Let's call T the solid torus, and you've got a simple closed curve gamma in its interior. It's the blue curve. Now you can consider a meridional disk, which is painted in red, that intersects gamma transversely. I've painted the meridional disk in a sort of very neat fashion, but it can be really very contorted inside T. So don't let the picture mislead you. I've drawn it so simply because I'm not good at drawing anything, but the situation could be much more complicated. Now imagine, we are going to count how many times the curve gamma intersects the disk, the red disk. And there are two ways of counting that. One would be an algebraic way, where we take into account the orientation of the curve. And so we count with a plus when the curve crosses the disk from left to right, and with a minus in the other sense, or vice versa, it doesn't matter. You count with that sign, if you count algebraically, In this case, the curve gamma intersects the disk in +1, -1, so 0 comes. So you would say that the algebraic intersection number of gamma and the disk is 0. And now you can also count geometrically and you just count how many points you have in the intersection. So we have 2 points. For reasons that I can't explain now, because there's no time, if we counted algebraically, we would just recover essentially check homology, and that's not particularly useful. So we are going to count geometrically. So we're going to say, we're going to take the minimum count over all possible meridional disks. So we imagine that you allow your red disk to run over all possible meridional disks. This beautiful sort of radial, nice flat disks, and also very contorted disks. And you minimize the geometric count of points of intersection. That's called the geometric index of the curve gamma in T. So in this example, the geometric index would be 2. It's one has to work a little bit to show that actually you cannot get less than 2 points of intersection. But the algebraic index would be 0. And that's partly one of the reasons why we prefer the geometric index, because it detects that there are 2 points of intersection, whereas the algebraic one wouldn't detect any points of intersection, although there are points of intersection. And if you have a pair of nested tori, well, you can define the geometric index of the small torus inside the bigger one as the geometric index of the core of the small torus inside the bigger one. So the geometric index has a very important property, which is called multiplicativity. And it just says that if you've got 3 tori nested, then, well, the formula there just says that the geometric index of the smallest torus in the biggest one is actually the product when you factor in sort of the intermediate torus. Now, why is this property important? Well, because, let me just skip that, because it can be used to show that this definition is sound, that it's correct. So if you have a toroidal set, then we're going to define the set of prime divisors of K as a set of prime numbers that satisfy a certain condition star for some neighborhood basis of K. And the multiplicativity property will ensure that it is actually, if it's satisfied for some neighborhood basis, it is satisfied for all neighborhood bases. So it says that or it implies that this definition is sound. And what is that star property? So look just at the first half of the slide, because we don't have time to go through the second part. So if you have a toroidal set, you can pick any neighborhood basis of K, which is comprised of nested solid tori, and you look at the prime numbers that divide the winding number or the geometric index of consecutive pairs of tori for infinitely many n's. This definition seems a little weird, but it actually, the use of prime numbers and the multiplicativity property, as I said, imply that whether a prime number P has the property or not, it's actually independent of the basis Tn that you choose. It only depends on the set K, the toroidal set K. And so it makes sense to define the set of prime divisors of K as a set of prime numbers that satisfy this. So for instance, if you have the dyadic solenoid, well, the winding numbers of all the tori inside the previous one are all equal to 2, and therefore the only prime divisor of the dyadic solenoid is P equal 2, because it divides infinitely many of the winding numbers, and no other prime divides infinitely many of those winding numbers. Let me skip to this slide already. So why are we interested, or why is this winding useful for dynamical purposes? Well, if K is realizable as an attractor, then as we said, it has a very special neighborhood basis where all the pairs are homomorphic. So in particular, all the winding numbers of each consecutive pair of tori are equal. And so when you compute the set of prime divisors, what you get is just the set of prime divisors in the sense of ordinary arithmetic. So the prime divisors of this integer big N. Or in other words, if a toroidal set can be realized as an attractor, then it has finitely many prime divisors. So if we can construct a toroidal set that doesn't have this property, so it has infinitely many prime divisors, it cannot be realized as an attractor. So we can do that to produce an example, and I'll finish with this. To produce an example, you can modify the construction of the dyadic solenoid by taking the tori. You still take a sequence of tori, a nested sequence of tori, but instead of having each torus wind twice inside the previous one, you allow the number of windings to change along the construction. And you can, in particular, you can construct them in such a way that Tn+1 winds P1 times Pn inside Tn. So the Pi are the prime numbers. It's an enumeration of the prime numbers. Then it's pretty easy to see that this sort of modified solenoid has infinitely many prime divisors, and therefore it cannot be realized as an attractor. And I think I'm done because I've used up all my time. So let me jump to the last slide. Thank you for your attention, and I hope you enjoy the remaining of the conference. And if there are any questions, I'll be happy to answer them.
And let's thank Jaime for the talk.
Thank you very much.
So are there any questions?
We have no questions. Oh, we have one.
Hey, so you mentioned that half of the Fox Artin knot could be an attractor, but the whole knot can't. And I didn't really see what the difference is in terms of constructing this torus with infinite genus. What difference does it make whether you have the whole arc or half of it?
You mean here in the Fox Artin arc?
Yes.
Well, it's actually, I cannot give you a sort of hand-waving explanation because it's so if you slice the arc in two halves and you look only at one of the halves, actually that becomes point-like. So its complement is homomorphic to the complement of a point. But when you consider the whole arc, its complement is not homomorphic to the complement of a point. And that's why, okay, so that's why one of the halves you can realize as an attractor, but not the whole arc. It's really counterintuitive completely, but it's like that. Yeah.
Okay, thank you.
Thank you.
Any more questions? Well, if not, let's thank the speaker again.
Thank you.
And I think we have a shorter lunch break today, so we will be back at 14:30, 2:30. Okay.